Hello everyone. We are going to be solving daily Leetcode problem given on July 20th, 1948. Delete duplicate folders in system. Like we always do, before starting this problem, we shall have a small motivational quote. If your code fails, refactor. If your architecture is flawed, redesign. If your approach is wrong, pivot. Many legendary success like Lamborghini after Ferrari came from iterating past rejections. Enzo Ferrari's rejection pushed Lamborghini to innovate. Similarly, failed tests, code reviews, and production issues are just signals to improve. The best systems and companies weren't built in one try, they were refactored into greatness. We have seen countless examples in our world where companies have not grown out of a single night or a one time effort. So they have been continuously refactored. Similarly, we should also take the same uh, take the same motivation to try till we become successful. And no task is too tough for anyone in this world, right? So keep focusing on your goals. Okay, with that being said, let us focus on this problem statement here. Due to a bug, there are many duplicate folders in a file system. You are given a 2D pattern paths where paths of I is an array representing an absolute path to the ith folder in the subsystem file system. For example, 1, 2, 3 represents the path 1, 2, 3 this way. Okay, that makes sense. Two folders not necessarily on the same level are identical if they contain same non-empty set of identical subfolders and underlining subfolder structure. We shall understand this statement better. We can. This is the key ask from this whole problem idea. The folders do not need to be at the root level and to be identical. If two or more folders are identical, then mark the folder as well as their subfolders. For example, folders A and B in the file structure below are identical. They as well as their subfolder should be marked. So let's say A has AX, AY, AZ, BX, BY, BZ. So all of the subfolder structure between the parent folder A is similar. So both of these folders are satisfying this statement that is being given here. Okay. However, if the file structure also includes the path BW, then the folder A and B would not be identical. Note that A/X would still be considered identical even with the added folder. Once all the identical folders and their subfolders have been marked, the file system will delete all of them. The file system only runs the deletion once. Not sure what this means. Might be so any folder that becomes identical after the deletions are not deleted. Okay. Return the 2D array answers containing the paths after remaining folders of the remaining folders after deleting all the marked folders. The paths may be written in any order. Okay. So this was a lengthy explanation, but if you remember our previous problem, we were only deleting subfolders if they were part of the parent folder. Like for example, yesterday when we had an example, AC, let's say, and ACD, we were saying we could ACD, we were saying we could delete this as this is a parent folder to this one, right? So here in this problem, what exactly is happening, one key difference is, let's say A has a subfolder C, and if there is another root folder with B which has an identical subfolder naming C, both of these can be marked for deletion. and once the file system runs deletion operation, then both these can be deleted, considering they are identical, they have identical subfolder structure. That's the whole problem gist. J- so we will understand this problem better through this example. So let's say this is like a root folder, right? So this is like a root folder, and these are all the first level folders, and these are their subfolders. If you see, A and C have two identical or similar subfolder structures, so mm, both of them will be deleted, and only D and DA will be returned. D and DA, these are the two remaining folders that will be returned, since these will be marked to be deleted. All of these and all of these will be deleted. Okay, so more or less we can understand the example 2 also quickly. So we are checking if a specific folder has a similar subfolder structure and any other node also has it similar. So this data structure should can be built by a data structure. This is a data structure that we can use to implement such kind of pattern, right? So this example also we can understand just by going through this uh, explanation here. Only thing, there is huge file list A, C, and AB, ABX, ABXY somewhere here, and W and WX. These are the two X and Y. Considering X has similar folder structure as W, we are marking these two for deletion, and the remaining folder structure will be other than these two, everything else is returned. WY is cancelled out and XY is cancelled out. So that's what is happening. So ACCB, the file structure is shown. The folders ABX and W and their subfolders are marked for deletion. So because they both contain an empty folder named Y. Okay. Note that the folders A and C are identical after deletion, but they are not deleted because they are not marked beforehand. So C, B, C, A, B. So these are the things that are deleted. Anything that contains X is deleted. This is deleted as well. So only thing that would be returned is AC and CB. This also will be deleted. So four different. These are the four folders that will be returned. Not too hard, but uh, if you remember the explanation that I said, this is all the problem statement is looking for. Problem is asking us to do. So there is lengthy description and lengthy examples, but it should not tire us out from understanding what is being expected from this problem. Okay, so I will I will start writing the approach that we can use to solve this problem. Before we do anything uh, bigger or any specific approach that we are looking to, as we looked at a specific example, I will write the specific example again that we are looking to solve. Maybe okay. So let's say this is our root path, and A, B, X, Y, C, and D, W, and Y. Let's consider this as a tree. Consider this as an example, and I am going to. This is similar to one of the examples that we saw in our lead code uh, for this problem. So x and y. So if we are required to delete, if we are required to mark a specific node to be deleted, then this is a set of node that we are going to delete. That's what we understood with the problem expectation. So these are the two nodes that would be deleted. These are the paths that would be marked to be deleted. So, and the most important thing here is this entire thing is a trie data structure. So if we know anything, or if we do not know anything on the trie data structure, I will try to uh, so we might be knowing that try it's similar to a tree where we are using the each value in a node is like a alphabet, and that's something that we see in the examples also. So a tree node or a trie node will have something like properties such as it will have a property of children, that is each node will have some children node, and let's say this will be of type map, and a serial or a subfolders that are under a specific node, and also we shall have a custom flag to delete or delete, right? And let us say this has initially false. So considering this, our each node we shall design our each of these node will take up properties such as this. If this is the last node, then this will have empty series. So for example, this doesn't have any subfolder, so this will take up empty, this will take up y, and this will take up xy, and this will take up bxy. So these are the, this will take up d, this will take up empty, and this will take up y, and this will be empty. So we are not really bothered much on this series at this moment, but yeah, once we do that, we shall uh, go over few steps. Our steps are or our series of operation steps would be, uh, first thing is we are going to build a tree, and then for build this tree data structure from the paths that we get from the input. From the input we build from the input path we convert to a tree data structure, that is we map over each for each path in of paths. So let's say our input paths will be something like uh, a ap, abxy. I just wrote this piece of the path, this entire piece of the path. So I hope you understand there would be other items in the array, such as uh, an array of consisting of single c and c d as the two paths. So we continue to build this input. We can continue to build this input, but uh, to make this entire input paths, this would be the paths, that input paths that we were talking about. Input paths. So with each path, we we try to convert it to a tree kind of tree try kind of data structures. We do it with this way. So let's say for each path, uh, we check if there is subdirectory of a specific path. If there is no node.children to it, then we add this node.children and dot set, as we have declared the children method for this try property as a new uh, map. So each try node will have a map, so we can say set or read or any such operations can be done for each of the children. So we set the directory, and this directory will be a child to this particular node or this particular path that we are looking at. And this again will be a try node, right? New try node, and we shall initialize a new class for it. So, and if this loop doesn't run, then we say node is equals to, we explore this particular directory, subdirectory, saying that there are children under this, and we dot get directory. We read the specific directory and we continue exploring this path, right? So that way we build the relation for each node and all the subdirectories that we get through the input path. And once we do that, we also need to populate the value. So this would fill out all the values for this children property of a specific try node. And next thing is we need to start populating what are the series or what are the different sub-series that a specific node or subdirectories that it has, right? So like for example, a specific node A has children such as subdirectories such as bxy, or P has xy, or W has a y subdirectory, and the last subdirectory will be marked with empty. So empty string. That's what we have looked at, right? For that we shall also be having a new function. Say so we shall be defining a new uh, serialize function which takes in a node, and it says if children size is 0 is equals to 0, then we define it as empty string, right? So that's what we've seen. Else if, then we form in parts or the different sub parts that we have. So we usually sort this serialization just to keep the consistency, and we say name and child of the node dot children, and we say we parts dot push name and serial. Okay, so that would be our serial. So that would give us all the subfolders that are present for a specific node. And once we have that, so we might do something like a join operation just to get the entire string. Instead of keeping it as a parts array only, we join it, let's say, in a simple string format with no thing. And if we also check here, only we can check if serial dot map we shall be defining another global variable, let's say uh, const serial map, just so that, let's say, serial map, this will be a new map. And the use of this one is, let's say, if x has a node y, we check if there is any other map which has a similar kind of subfolders. Let's say y in this case is also corresponding to a key of w, so we can mark these two nodes as to be deleted. And that's what we are going to do here. We are going to check if serial.map has a serial subfolder, then we mark to delete as true, and also this current node that we are looking at, also we mark it to node dot to delete to, and the specific serial map dot get the specific node and mark that also to delete. So the specific node where we are calculating this subfolders, also the other folder which already had the same subfolder structure, we get it from the serial map, and also we mark it to be deleted, right? So this helps us for our next stage, where, let's say, uh, once we have marked all the try nodes that are to be deleted, we can simply do a dfs or a in order traversal. Let's say we can initialize a dfs function which runs through all the nodes and paths uh, that we have. And let's say for each name and child in of node and children, node dot children, if we can say a result array which we need to return, this will be the output that says after deletion. So as the problem says, after deletion we need to return all the valid paths, right? If does not have the flag to delete, if it is not marked as to delete, then we push it to the result dot push the specific path, and we continue dfs to its to its children, and also we send in the path. So this is the dfs path, and that way for each path we also do a pop operation. And the initialization of this dfs will be a simple uh, let's say a simple root and also a simple array, and finally we can return this result that we are looking at. I know there was a lot of discussion here. It might be a lengthy one, but I would say just understand whatever diagram that we have drawn here and learn how the try data structure works, because this problem, I believe, is asking us to be implemented in try data structure. Also, let me know in the comment section, uh, can we even solve the previous problem? I don't know if you remember the previous problem which was given. To be exact, it was July 19th, daily Leetcode problem, which also required us to delete subfolders. So could it also be solved with a tree data structure, right? So do let me know in the comment section, and I would say just have a refresher or a glance or a new understanding if you are beginning to learn try data structures for the first time, look into it and just come up take up this problem uh, to solve this problem, right? So with this explanation, I would go to the lead code editor and quickly code this up and uh, complete the solution. Okay, so now let's start coding it up. So this is a function where we have defined certain properties for each node, and we have defined a root node here as, let's say, this for this example that we have seen in our drawing board as well. So now we are going to build the input paths that are given to us with this entire tree node using this function, right? So for that we are going to do this. So once we do this for loop where we iterate through each path, and for each subfolder, for if there is a subfolder for each path, there will be a subfolder. Let's say, for example, this is a folder, and if the specific node doesn't have any if it doesn't has this folder, then we add it to it. Else, if this already if this uh, if there is already a folder, let's say a, and if there is new path, let's say ab, then we consider a as a node, and then we add b to the a, or a as a as a node, and we add this subfolder path ab. So that is what we are doing with this for loop here. uh, Now it's time for us to do the serialization part, or to calculate all the subfolders. Let's say A has a serial B X Y, so that's what we are going to do. And we are also going to initialize that serialized map, which is going to help us to mark if a specific node is to be deleted or not. So that's what we are going to do. So this is a condition where if the specific node has no children, then we simply mark it as an empty string, saying that it doesn't have any subfolders or children's or child nodes under it, right? So, so we are always going to sort each node with all the children values being sorted, such that, let's say, if a b a b so let's say, for example, if there are nodes such as, if these set of values were given earlier, then we still would have lexicographically sorted nodes such that a c y, and here also it would be a b x y. So this children also will be in increasing order, and also this first row will also be stacked up, such as in increasing alphabetical order. That's what this is going to help us with, right? So this is going to help us for the uh, serials array, or this is going to give us all the subfolders for a specific node, and then we can assign the node dot serial property to this serial array as a string. We can convert the serial array as a string, just like this. And here we also make a check if there is any, say, any similar subfolder structure in a different part of node, then we mark the specific node and also the previous entry in the serial map node to also be marked as deleted. So once we have serialized the root node that we were intending to fill up this part of the value and the children's value and this deleted value also being marked, now we can run a simple DFS or a in order traversal such that we can go through each node and then we can filter out all the possible values that are not to be displayed in the result. Like for example, this is the output. So where C and B and A and B are the only two output, and these two nodes X and Y are deleted, or A B X A B X Y are deleted. So this node and also this node, all these four will be deleted. So for doing that, we have the deleted uh, property set to true. So we can filter out all those nodes and we can have a result array which So we can initialize this GFS with the root or the input uh, tree node data structure that we have built, and an empty path, so that we start populating all the values into the results array, and we can simply return the results array here. Okay, this should solve our problem. Let us try submitting this. Okay, so line number 25. Cannot read property entries. Children dot entries. As you can see, the solution gets submitted. Time complexity of the solution would be, building trees would take uh, n into m, let's say l into m, so number of paths into the total number of subtrees, and serializing the tree would take about n into l being the subfolder length, and DFS would also take n into l, maybe the subfolder length. So our total time complexity would be n into l, and space complexity would be n into l again, because we have a results array which is like a, again, like a, so array of arrays. So it would be n into l, where n is the number of paths and also a subfolder for each path, right? So that's about the time and space complexity. Hope you found this video helpful, but please do let me know in the comment section if this same try data structure can be used to solve the previous problem as well. Let me know if you have any doubts or any specific uh, piece of code snippets that you want me to explain better. Let's keep the comment section going. I would be happy to hear from you. Thank you.